Okay, so we've drawn these. They're hard-coded. We need a way to manage what room the player is in, what doors are valid to be drawn, and what doors are open in specific rooms but closed in other rooms. So each room is unique, has a unique set of doors, and they can either be open or closed. So we want to keep track of those states like within a byte, and each bit could represent if a door is open or if it's closed. It actually happens that we have more than 8 doors, so we need more than 8 bits, so 2 bytes will represent all the doors. And let me just kind of visually show you what that's going to look like. So we have 9 rooms, and we have each room has a unique set of doors associated with it. So room 0, for example, it contains a right door. It also contains a bottom door. Now, room 5, for example, it's unique in that it only has a top door, a left door, and a bottom door. Now, this is all fine and dandy, but if we consider room 0 here and room 1, it has a left door, or room 1 does. It has a right door and a bottom door. But if we look at this door in terms of being one particular unit, and being represented by 1 bit, it's going to be useful because that's literally the same door. It may be the left sprite in room 1 and it may be the right sprite in room 0, but it's literally the same portal into the other room. It just flops sides because you're traveling from room to room. So we need to think about these not in terms of this is one door because it's the left of room 1, this is another door because it's the right of room 0. No. We need to think of this as one single door. So in total, we have 12 doors, and that's these here. So in order to put these into bytes for storing their state, like on, off, open, closed, barrier, not a barrier, we need to group these. So these are going to be 8 doors, so 8 bits. That's going to be in its own byte. And then we have these 4 stragglers here, which can occupy half of another byte. So let's actually create those in our RAM. So this is going to be door states 0 through 8. And then door states, what were they? 8 through 12. 12 is B in binary. So 8 through B. Okay, I think that's easy to understand. We also don't want to be hard coding these doors. So right now, all it is doing is loading them from this table and loading them in the setup routine. It's just putting them in RAM. But if we want to be able to dynamically remove them, draw them, remove them, draw them based on where the player is, they need designated spots in RAM that we can reference multiple times. So let's designate where those places are going to live. So top door RAM is going to equal the next slot available. So we're up to slot 7 already. So I shouldn't call it slot. Position 7 in RAM. So sprites offset 8 is where this one starts. Now, how many actual bytes is associated with the top door? So we have 4 sprites, 4 bytes each sprite. That's 16 bytes total. So the next offset we need to actually find for the bottom door RAM, this is bottom door, is going to be 16 past 8. And these are in decimal. Pretty quick math, but I'm just going to get the calculator out. 8 plus 16 is 24. So 24. The next one is going to be the left sprite. 16 past 24 is 40. The next one is going to be the right most door. 16 past 40 is 56. So those are going to be locations in RAM we can constantly reference. And I also want to, while we're here adding stuff in RAM, I want to add one more thing. So where are we? So in this calculate room index function, we took the Y index, the X index, calculated where the player is in each room, but we've only stored it in the X register for all this indexing stuff into the collision and into the rooms. If we do anything beforehand, before we load all this room stuff and we upset the X register, all that's going to break. So I'm just going to quickly save that into another variable. I'm going to call it p room index, just so we can load it again when we need it. And for now, I'm going to load it here. So load x p room index, just so we don't break anything. Okay, I think I missed some stuff when I was equating these to a spot in RAM. So let's just add room and put all the values down. Index, p room index, set 0C. This is 0D and 0E. Okay, that should be all we need. Actually, no. I know we're just adding a whole bunch of stuff. There's not a lot of assembly going on, but this is crucial to what we're about to do to make it all as readable as possible. So what we're about to do is after collision, we're going to go JSR check load doors. And what happens in load doors? We're going to compare the p-room index, but then we're going to eventually have to load door states, and we're going to use the AND operation to compare with specific doors. So like, let's say I want to target door 0. Door 0, for example. This one right here. Now, when we packed all these doors into bits, this door 0 was this first bit location. Door 1 was this other one. Door 2 was maybe this one. And then it goes down the line. So rather than doing a bunch of load door states, compare with this obscure binary number, load door states, and with this obscure binary number, let's make some aliases just so we can read this in better plain English. So door 0 is going to equate to a numerical binary value of this, the first bit on and then the rest off. And we're actually going to do this 12 times because there's 12 doors. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. That's 1, 2. Okay, and then this just bits over. This bits over. And then once we reach the end of that byte, we're on to the next byte. And we just increment these over. Okay, now this is going to allow all of our code to be much more readable. Okay, now we can code. I know we've technically been coding this whole time. It's all part of the same goal. So let's actually write this CheckLoadDoors function. I'm just going to put it all the way at the bottom here. Just compartmentalize in my mind. I kind of want it to be down here. Okay, so what has to happen? First off, we load the player room index because we want to find out what room they're in. And if the value is 0, they're in room 0. If the value is 1, they're in room 1. I think that's pretty easy to understand. So we just need a big comparison tree. So if the value is 0, we can just straight ahead break if equal or break to equal. And this is going to be room 0 doors. And in room 0 doors, that's where we're going to check if a door is on based on its state, draw if it is on, and not draw it if it's off. So in room doors, so in room 0, for example, what doors are present? Each room is unique, mind you, so we have to have one for each room. So we have a right door, and we have a bottom door. let's just kind of write this as some supplementary notes. Door 0 contains right door and bottom door. Okay. Now right door, what does that equal? Well, the right door of room 0 is 0. So let's record that, 0. Now the bottom door of room 0 is 2, and that's going to be unique to room 0. Bottom equates to 2. So these are just notes I want to have here so we can reference them very easily. Okay, so we load the door states. And these are the first couple doors, so it's door states 0 through 7. Now here's that AND operation, and we want to compare which door are we going to check first. Let's check the right-hand door first, and that's door 0, mind you. So AND with door 0. If the AND operation yields a 0, that door is open. So break if it is equal to the plus sign, and we skip drawing the door because it's open. And we can return from subroutine. Let's just get this door working first, and then we're going to do the bottom door. So what happens if this is toggled on, for example? So if this yields a 1, we're going to be in this section of the code, and we're going to jump to subroutine, draw right door. And this function we're going to be able to reuse over and over again just to kind of keep our code tidy and small. And let's draw this. So what happens when we draw the right door? We want to load an index and a counter with 0. So we initialize y. I'm trying to steer away from x just in case. I know we have that p-room index to retain x's value and just reload it, but if I can steer away, I want to do that. So we loaded x, and then we're going to need a little loop. So I'm just going to use the minus sign. It's an anonymous label. Instead of writing out draw right door loop, which is kind of long, I'm just going to use the minus sign. It's just tidy. I know it's a loop, so I'm just going to keep it like that. And then we load. What are we loading? Remember, we have our door Sprite data. I don't know what I was about to say, tablet data or something. We have our door data over here, so we've named it top door, bottom door, left door, right door. So load right door index y. And this is loading Sprite data. And where are we going to store that? Remember, we designated where those live in RAM already, so we're going to use right door RAM. And that's at a specific Sprite offset. Also, I'm glad I went up here because this is Sprite RAM and not Sprites. Sprite RAM, Sprite RAM, Sprite RAM. That would have been a gotcha if I didn't scroll back up. We would have found it, we would have fixed it, but it's just easier going catching it now. Okay, let's go back down here. CheckLoadDoors, draw right door. Okay, and we store that in right door RAM. Oh, index y, index y. And store in door RAM. And then we increment y, compare y with how many bytes are we writing? So we have 4 bytes, 4 sprites, 4 times 4 is 16. Compare with 16. Hexadecimal, it's just the number 10. And then we break if it is not equal back up to the anonymous loop label. You can use it for other stuff. I usually use minus signs for loops. And then we return from subroutine. Okay, so this should draw the right door of room 0. Actually, no, we haven't ticked the bit on. Also, we have an error. Let me see what that error was. 552 unknown label. 552, 552. Door states 0 through 7. That should be a label. Door states 0 through 7. Did we misspell it up here? Oh, 0 through 8. That needs to be 0 through 7. Because counting starts at 0. 8 bits makes it to 7. So that should have fixed that. But I also noticed that we are still drawing all of our doors, just hard-coded. So let's put this total sprites value back down to 2. So we should have no sprites. And we should also have no door in room 0 just yet. But all the framework is there to where now all I literally have to do is toggle a bit, which is the ultimate goal. So we're loading door 0, which remember equals this number. And we're going to store it in door states 0 through 7. Okay, moment of truth. We're going to travel to room 0 and see if this draws. It didn't. It just drew straight away. We have something completely wrong. Let's actually just travel to 0 and see what's going on. Okay, let's fix this. Did we not index into p-room index? CheckLoadDoors. Oh, we don't have a return from subroutine here. So we did this branch and it spilled over into room 0 doors no matter what, because we loaded the index, we branched if it is equal to room doors, but if not, it escapes this branch and just falls into room doors. So we return from subroutine here. And now it should not draw the door. Now, moment of truth, we're going to room 0 where it should, bam, it drew the door. So step 1 complete. We need to do this for all of the rooms and all of the doors in those rooms. And we also have to do one more thing, which I can demonstrate now. Look what happens when I leave this room. The door remains because we've never just erased them to start with a clean palette. So let's quickly do that. So when we load room, before we do anything, jump to subroutine, let's clean the door RAM. I can just put that up here, I guess. Clean door RAM. So what has to happen? I'm going to load the accumulator with the value FE, because that moves the sprite off the screen. I'm going to load our index with 0, and this is also the counter. We're going to make a loop. We're going to store in where is the first index into sprite RAM where all the doors live. So that's sprite RAM 8, sprite RAM offset 8. And top door is the start of that. So we could just put top door as our label and then index however many bytes we have, which 4 per sprite, 4 bytes per sprite, 4 sprites per door, 4 doors. It's going to be 4 times 4 times 4, I think. 4, oops, make sure I'm in decimal. 4 times 4 times 4. Oh, I just clicked hexadecimal. So 4 times 4 times 4 is 64. That looks right to me. So 64. Let's go back to that function. So we store in top door RAM, index y. We increment y. We compare y with 64, which in hexadecimal is 40. And that's all of those bytes regarding every single door and every sprite regarding the doors. Branch if not equal to minus sign, return from subroutine. So this should remove that sprite when we're not in room 0. Dun, da, da, da. We've drawn it. Okay, let's move away from this room and the door is magically gone. So this is the core mechanic for making sure that 1 bit represents the state of 1 door. And we basically have to replicate this 9 times per every room. I'm going to see you in the next video. I may do some of this off camera. I may record it and put it up. It's just a lot of doing the same thing. So I'll see you in the next video. It may be more of this. It may be something that's more progressed. I'll see you in the next video though.